Hi everyone, I'm in this conference to share what we have been working using SIMBA simulation platform. So the title of this presentation is Residential Microgrid from Theory to SIMBA Simulation and Experimentation. This work has been performed within the National Engineering School of Tunis, Tunisia, of University of Tunis El Manar, and more specifically within the Microgrid platform. The agenda will be as follows. First, the context and motivation. After, I will describe a case study and the model development. Finally, I will present some results and conclude with future work. So, the context. The fast increase of PV rooftop leads to new challenges for low voltage distribution networks. Power quality and grid voltage stability are crucial ones. Many kinds of solutions are under investigation. They can be grouped into three categories. The first includes additional equipment, such as battery energy storage system or BESS, or such power quality improvement devices, PQID. The second category is about concept, collective self-consumption concept, and microgrid concept. The last is advanced control for inverter-based resources, IBR. So, an experimental platform has been developed for research, development, and training purposes. It is flexible, modular, and scalable, and it is built with commercial equipment. The diagram of the setup is illustrated here. The platform reproduces a three-phase, four-wire distribution line with a 15 kVA transformer. There are 5 connection points, a three-phase one at each end of the line, S1 ABC and S2 ABC. We can connect a three-phase PV system or a BESS or a three-phase load at each of these connection points. There are also 3 single-phase connection points, one at each phase, corresponding at a residential house. So, house A, house B, and house C. House A is only consuming, while a 3 kilowatt PV inverter is installed for each of house B and house C. House C is also equipped with a storage system. At the beginning, technical topics aimed to investigate are, first, operation of PV systems and MPP control with no reactive power exchange. Such PV inverter operating is the most common one. The second point was power quality issues, and more specifically, the imbalanced situation and voltage deviations due to single-phase residential situation. The third was data collection and analysis, so the energy meter location, data in cloud, and data analysis. Afterwards, the objectives evolved and focused on two main points. The investigations then concerned, on the one hand, solution for power quality issues mitigation, with the 3 main groups of solutions already mentioned. And, on the other hand, the integration of the laboratory developed components. The challenge was the validation in a meaningful environment, a single component result of our research. So, the methodology was to start from our experimental platform, then to develop its SIMBA model, and to integrate in this microgrid model the SIMBA model of the equipment in the development, EUD. A real-time simulation is then performed for this EUD, and tested with the power hardware in the loop PHL approach as a single component. And finally, at the last step, PHL component will be integrated in the real platform. The real microgrid platform for first SIMBA model is shown here. The distribution network and the transformer are replaced by a 20 kVA grid emulator that can emulate grid faults. It is modeled by an ideal AC source. At first, only linear loads are considered. PV systems are modeled as controlled current sources where the reference current is determined by a given input active power. The reactive power is null. Also, at first, impedance lines are set the same, with a common value. A three-phase power analyzer is set at each connection part. Here, an example how to integrate into this platform an equipment under development. In this example, the EUD is a three-phase system that can be a PV system or bus system. And the investigations were about developed advanced controls. The simulation challenges for such platform are of various kinds. Slow and fast phenomena, many variables to consider for energy management global system, many scenarios to consider for validation a new feature in a meaning way, need to combine simulation of phenomena with optimization algorithms based on analytical equation, fast simulation despite complexities. Let's now move on the case study. It concerns a smart load and an electrical spring. But first of all, what is the problem? The widespread integration of photovoltaic systems leads to unacceptable voltage drops for critical loads. The concept of smart load, considered as a smart grid technology, makes it possible to maintain a constant voltage at the terminals of this critical load. A smart load consists of what is known as an electrical spring and a no-critical load. The non-critical load, connected in series with the electrical spring, will absorb voltage fluctuations. The electrical spring, consisting in a DC-AC converter, is controlled to maintain constant the smart load output voltage. The power structure of the smart load and the electrical spring are detailed here. An equivalent circuit in S-domain has been established to design the control. More details and results have been published in this paper. The complete control diagram is shown here. Based on the RMS reference value of the voltage at critical load terminals and its regulation, the instantaneous reference voltage at the terminal of the electrical spring is generated. Next, cascade regulation using resonant proportional controls is used to obtain the current that must flow through the electrical spring capacitor. This is then used to deduce the reference current of the inductance. Regulating this current makes it possible to generate the modulation index and then the control signals for the DC-AC converter that constitutes the electrical spring. A PLL is used to determine the phase angle of the voltage across the critical load. This angle is a key element in generating the reference voltage across the electrical spring. This schematic diagram is the same as the one reproduced with SIMBA. The first simulations were performed using an average model of the DC-AC converter of the electrical spring. In this case, the control provides the voltage that must be generated by this converter. Here we see the grid AC source where variations have been programmed, line impedance and power analyzer, the critical load and the no critical load. The control is first validated with this average model. In the next step, the average model is replaced by the instantaneous model. At the control level, we just need to generate from the modulation index the control signals of the power switch. The simulation results correspond to a mains voltage initially set to its nominal value. At 1.5 seconds, the voltage increases by 10%, and at 1 second, it decreases to 95% of its nominal value. The first two curves illustrate how the RMS voltage across critical loads returns to its nominal value after transits last about 100 milliseconds with variation about 10%. The following curves display the voltage regulation across the electrical spring terminals, VUS, and the regulation of the converter output current flowing through the inductive filter LF, with detailed zoomed views. The SIMBA model of the smart load developed in this way are then integrated into the other microgrid SIMBA model. However, in order to fully highlight the contribution of smart load, realistic voltage drops must first be created at the connection points, which requires the necessary line impedance values. We have identified the ones of our experimental platform resulting from cabling, but they are not relevant to our needs. A separate study is being conducted to calibrate these choices and add them to the actual platform. In addition, to quantify the contribution of smart load, we need to program specific voltage stability indexes, such as the fast voltage stability index methods or others. Ultimately, the objective is to develop energy management systems, first at the SIMBA model level of the platform, then on the actual platform. Regarding smart load and its integration into the actual platform, we first moved on to the real-time simulation with programmed control on the CPU part of our simulator and the rest at the FPGA level. The results were published in the paper cited on this slide. We are currently testing the PHL approach in which smart load is in the simulator and the voltage at its terminals is amplified to be connected to a critical load, to a real critical load. Next, we aim to include this smart load in the actual platform via this power amplifier. The idea is also to compare it with the commercial component designed by IBR for automatic voltage regulator, which is becoming increasingly widespread on the Tunisian market as a solution to voltage drops caused by the massive integration of photovoltaics into the distribution network. I am now coming to the end of my presentation, and thank you for your attention.
Thanks a lot, Ilham.